Good morning. In my presentation, I'm going to talk about the numerical modeling of residual stress and deformation during the powder bed fusion process. In the presentation, I'm going to talk about the metal 3D printing methods. I'm going to outline them briefly. Then I'm going to discuss how the ANSYS models the process. Then we are going to try to estimate the maximum total deformation, maximum strain, maximum equivalent stress parameters with our ANSYS simulation program. In the results section, I'm going to discuss for different outer wall diameters, for different head spacing, for different deposition layer thickness, and for different preheating temperatures, how these three parameters, maximum total deformation, maximum strain, and maximum equivalent stress, changes. As you know, additive manufacturing methods were developed basically for polymers, and they were used to manufacture the prototypes. Generally, these parts were not very strong, and they were not used in many applications. However, with the time, these methods improved, and also new methods came up which use the metal particles or metal wire during the manufacturing process, and these methods were able to create metal parts. And the strength of the parts today are acceptable for many engineering applications. If we look at the major metal additive manufacturing methods, we see the powder bed fusion, direct energy deposition, and binder jetting. In the powder bed fusion or laser powder bed fusion process, a laser beam is directed to top of the powder bed, and it solidifies the particles where we have to build the part. So at this top layer, it is going to move around, and wherever we want to create the part, it is going to bind the particles here. Either it's going to sinter or melt. It could be laser or electron beam. And it's not going to touch the other areas. After the layer is created, this table is going to move down, and this table is going to go up, and it is going to bring here some powder, and then this roller is going to move, and it is going to create a new powder bed layer to manufacture the part. When we use this method, the envelope is pretty limited. Direct energy deposition method uses a system which is shown here or here. In this case, we are sending metal powder, and then with the laser, we are creating a bead, and we are creating the part as a bead. Or we may use a wire feed, and with the laser, we melt the wire and we attach it to the locations where we want, and we create the part. If we are going to attach this head on a robotic arm, we can extend the reach of that arm, and we create much bigger parts. Binder jetting method, instead of laser, it uses liquid binder, and it works similar. This powder bed mechanism is similar to the powder bed fusion method uses, but in this case, instead of binding the particles with the laser beam by melting or by sintering them, we use a glue, and we attach the particles to each other with a binder. And in a similar way, the table is going to go down. We are going to bring more powder here. We are going to create a new layer, and we are going to put the liquid binder at the proper locations to create our part. Now, the laser powder bed fusion and direct energy deposition are the most commonly used methods. Powder bed fusion is very precise, and the layer thickness is smaller. But as I mentioned, the built envelope is small, and the manufacturing process is very small. We can obtain good surface finish and good feature resolution. Direct energy deposition method is not as accurate as the powder bed fusion. However, we can generate much larger parts, and we can do the manufacturing much more faster depending on how much powder we are going to direct to the locations we want to generate our part. But the dimensional accuracy and surface finish, also the feature, the resolution is much worse compared to the powder bed fusion. In manufacturing, conventionally, we consider that a part design is going to be prepared, and then we are going to prepare the 3D printing program. It is going to be given to the machine, and we are going to get our product. However, especially for metal 3D printed parts, the failure rate is very high. So for these, we may see that the part is not acceptable, and it is necessary to build it again. So instead of manufacturing the parts again and again, it is a good idea to simulate the 3D printing process and to see what kind of results we are going to get, and according to it, to make the proper changes. Now, if it is possible, we just change the operational parameters, and then with the better operational parameters, we can manufacture the part on the additive manufacturing machine with good quality. But sometimes we see that whatever we do, the operational parameters are not going to be good enough to get the quality with the results we want to get. In those cases, it is necessary to go and to change the part design, to make the part design in such a way that it is going to cool maybe faster. We are going to create some pathways for the temperature distribution. So it is possible to modify the design to obtain a better quality. In this study, we used the ANSYS finite element program. ANSYS finite element program has direct energy deposition, laser powder bed fusion, and metal sintering simulation capabilities. ANSYS uses a finite element solver. It first models the thermal system for the given structure, and it will estimate the temperature variation in the system, and based on it, it will estimate the strain of the parts in the process. Although it looks relatively simple, there is a wizard which helps the user. However, it is necessary to have some experience Otherwise, the models fail very often. It is necessary to set up the system very well. I'm not familiar with this process that much because always my students and other friends were involved with this process. In this study, we simulated 90-degree circular manifold. We considered that we are going to manufacture it by using the Inconel 718. The build plate was 316 stainless steel. The building parameters are presented here, and we created the mesh with the 2 millimeter layer height and element size. First, a calibration process was done, and then, as I mentioned again, the finite element solver worked, and it created the temperature field, and then the static model estimated the stress and stress fields. These are the simulated models. These are animated. You cannot see them here because this is from the PDF. So in this study, we looked at the maximum total deformation, maximum strain, and maximum equivalent stress. So we evaluated if we have different outer wall diameters, how these parameters would change. So when we increase the outer diameter, we basically increase the part thickness and the heat concentration increase. So all the critical parameters we considered have an increasing trend. We looked at the different head spacing. The head spacings is the different distance between the beats the laser create when we scan the surface. So in this case, if we increase the head spacing, heat concentration decreases, and as a result of it, the parameters which we consider are going to have a decreasing trend. When we looked at the deposition layer thickness, again, we see that the heat concentration is going to decrease when we increase the layer thickness, and it is going to help us to reduce the critical parameters which we consider like the total deformation, maximum strain, and maximum equivalent stress. Also, we looked at the preheating temperatures. When the preheating temperatures increase, the temperature gradient in the melting region decreased, and as a result of it, we obtained better or lower maximum total deformation, maximum strain, and maximum equivalent stress. So if we outline all the presentation, we saw that it is possible to simulate various parts. It is quite time-consuming process, and it needs some expertise. However, it is much better than manufacturing a part in 24 hours and then to figure it out that it's not good enough. We saw that the outer wall diameter and wall thickness increase. It's going to make the maximum deformation, maximum strain, and maximum equivalent stress increase. On the other hand, increasing the head spacing and deposition layer thicknesses, then the maximum deformation, maximum strain, and maximum equivalent stress are going to decrease. And again, increasing the preheating temperature reduce the maximum deformation, maximum strain, and maximum equivalent stress. So it is possible to add the supports to the part geometry to enhance the thermal path, and in that way we can avoid the heat concentration. So it is a good idea to run the simulation and to see if just changing the operational parameters, if we can get the part with the desired quality. If we can't, then we have to go and we have to change the design.